Maybe we can start. I'm very happy to have Afonso from ETH Zürich. He graduated a few years ago from Princeton, and then spent a few years at New York, and then finally decided to go back to Europe. And he has done some fascinating work at the intersection of a statistical computational trade-off, which I'm a great fan of. And today he's going to tell us more about this line of research.
Thanks so much, Amin, for such a nice introduction. Thanks so much for inviting me to speak here. It's a pleasure and an honor. So my talk is sort of divided in a very general audience part, and it gets a bit more specific towards the end. And I'm happy to, stick around for as long as anyone is willing to listen to me to discuss, or willing to discuss with me for after the talk. So I'll talk about statistical to computational gaps and sort of limits to learning, both statistical and computational. And then in the end, I'll get a bit more into things, in particular quiet plantings, which is something a bit newer that I'll describe at the very end of the talk. And so let me just start with sort of the very, very broad introduction. So I used to start with an explanation of why understanding the mathematics behind data is important. I think this is no longer necessary, and I'll just let you enjoy a cartoon. Cartoonists capture these things much better than we could ever could. And so what am I interested in? I'm interested in the very sort of mathematics side of this. So in particular, I've been interested in trying to understand lower bounds, or trying to understand what cannot be done with respect to learning and inference and so on. And so I want to understand what are the limits of what one can learn, and which methods work and why. And here I'll let you also enjoy an incredibly clever cartoon from XKCD, as they usually are. And I want to know, why do methods work? And in particular, what are the bottlenecks, or what makes a problem difficult? Is it the quality of data? Is it the amount of data? Is it the fact that we don't have enough computational power to retrieve information from data, and so on? And towards the end, I'll talk a bit about evaluating and in particular certifying answers from, or if you have a certain task, such as inference and parameters, how much can you certify how well you've done in the past, in after the fact, a posteriori, and how much are there bottlenecks for certification, and what do they look like? So before we get into that, let me just give a sort of a brief history of this side of of mathematics and of trying to understand the limits to learning. And there's sort of two sides to it. There's a statistical information theoretical side and the computational side. So of course, we haven't had computers for that long. So of course, the statistical side is much, much older, and it dates back several centuries. And the central question here is, how can we understand how much data we need to retrieve a certain piece of information, or to learn something about that we're interested in learning about the world? Right. This can already be seen already in the work in the 70s. The whole notion of Bayesian statistics and of computing a posterior and having a certain uncertainty in the posterior is very much present there. This notion that if we don't have enough data, maybe we can't learn with completely exactly. Right. This of course got much more matured in the last 100 years. And there's a few extremely important notions. Of course, there's many other pieces of progress that were very important, but it's worth mentioning things like Fisher information. Right? Fisher information attempts to capture how much information does a sample or a data point have about a parameter. It's a very sort of local notion, but a very important one nonetheless. Right? And sort of hypothesis testing got very well understood mathematically, at least simple hypothesis testing in the 30s by the so-called Neyman-Pearson lemma. Right, so you should view hypothesis testing as learning in a simpler world, where you know that there's only two possible states of the world. It's either A or B, and all you have to do is decide which one you're in. Right, and all this got a bit more formalized for statistical estimation, where there's not just two states of the world, but you actually want to estimate the value of a parameter. And things like the Kramer-Rao bound and so on started showing up maybe now 70 years ago or so. Then around the 40s was the appearance of information theory and the work of Shannon and Hamming and so on, where you start having a notion of measuring information in a much less local way, and be able to answer questions of the style of how many bits of information do we need in order to identify a draw of a random variable and things of this style? And then since then, there's been lots of other things that are very important. I'll mention minimax, contiguity, and so on. But all this impressive work is trying to answer the question of when is it that there's enough information in the data? Right? When is it that the data contains enough information for me to learn what I want to learn, to either do hypothesis testing or statistical estimation, say. Now, this is not the end of the story, right? Because almost always when we're trying to learn to do estimation, we have to do some form of optimization problem or some form of computational problem, right? We have to find a parameter, a signal, a model that best fits the data. This can be maximum likelihood estimation. You can be training a neural network, but at the end of the day, you need to solve some form of optimization problem to maximize a notion of fit or minimize the notion of error. And the very natural question, of course, is as our data gets bigger and bigger, are these computational tasks feasible or not, right? This is not a question that was asked 300 years ago, but much, much more recently. And we know that there are problems that we believe are difficult, that they're inherently difficult, right? The classical example being the knapsack problem. Right? And we know that some problems that may arise, so we know that there are some problems that we believe are difficult, right? I don't want to get much into complexity theory. I don't think I have to for this audience. But the natural question, of course, is, do the problems arising from learning, are they computationally hard or not, right? And again, I did my homework of doing a bit of history, and actually this notion of computational hardness, or the question even of, are there problems that are intrinsically hard, that are difficult for a computer, dates back to the 50s. I highly recommend, if you haven't, to look at this letter that Gödel wrote to von Neumann in 1956, where essentially he asks, I mean, it may be in other words, whether a computer could replace a mathematician and find proofs of theorems efficiently. Right? And it's just an amazing thing to read, I think. And of course, this got much more formalized in the 70s, where we defined, or Cook and Karp and so on defined what the notion of NP hardness, a class of problems that we don't quite know for sure if they're hard or not, but we have very strong reasons to believe that they are, because if we could solve one of them, we could solve all of them. And people have been trying for very long and haven't succeeded at solving any of them efficiently. But the point of all of this is that if we design the whole way learning is done and statistical estimation is done, is we build some kind of model, and then we try to find a parameter that best explains the data under this model. Should we be building models such that the resulting optimization problem is easy? It seems common sense, because if we don't do that, then we wouldn't be able to solve the problem in the computer as the data grows bigger and bigger. And so it certainly motivates that one restricts ourselves to problems where the resulting computational problem is easy. And this is one of the reasons why people tend to look tend to include things in their model, such as linearity and convexity and so on. It's not the only reason, but it's certainly one of the reasons. Right? But we know now that we sort of dropped this requirement and now work with models on which, neural networks being an example, but there's many others, on which we don't know for sure that the resulting problems are easy. Still, somehow they seem to be okay, and we seem to still be able to solve them. And this is something that we want to understand, both why is it happening in some of the models and problems where it does happen, and can we be pretty confident that it will not happen in some other problems, for example. Okay, so let me now give you an example that's sort of very close to heart to illustrate some of this. Okay, so this is the community detection and stochastic walk model. So the goal here is to recover communities on to find the communities in a graph. And here, what we're going to do is we're going to have a very simple generative model, right? So that we understand everything about the data. And now we can ask a very precise question of when is it that we can recover these communities from this very well specified model, right? Because then we can do math around the model because we understand it very well. Okay, so the model is the simplest possible model with community structure. You just have a graph with n nodes. Okay. The nodes get split randomly, n/2 to one side and n/2 to the other. So you split, you put n/2 on this side and you put n/2 on this side. You color one side blue, the other side red. And now you draw a random graph with the following rule. Every two nodes on the same side get connected with probability P. Same thing here. Every two nodes across get connected with smaller probability Q, right? So we think of Q as smaller than P. Okay. Now, clearly, this graph will have a certain community structure, right? These nodes will be more connected and these more connected, and there'll be fewer connections in between. And now you can ask, when can we recover this structure? When is it that sort of P is big enough with respect to Q such that you can actually learn this structure from just the graph, right? So one way to formulate this question, of course, is after we build this graph, we jumble everything together, we take away the collars, and we ask, can we recover the collars, or in particular the partition? The meaning of blue and red, of course, went away, but we ask, can we recover the partition? Right? Clearly, if P is the same as Q, we'll not be able to do it. If P is much, much larger than Q, certainly seems easy, and somewhere in between will be an interesting regime. Okay, so you sit down, you try to work the math of when is it that there is enough information in this graph to be able to recover the partition, and you get to the following theorem that turns out the interesting regime. For those of you used to working with random graphs, this will not be a surprise, right? This is around the connectivity regime, but turns out the interesting parameter regime is when the average degree is logarithmic. And so if the probability of connection within the same community is alpha times log n over n, and the cross community is beta log n over n, then one can show that if this simple equation gets satisfied, so if root alpha minus root beta is bigger than root 2, then it is possible to recover the true communities. In particular, the algorithm that recovers the true communities is the simplest possible, or maybe not the simplest possible, but the first thing you would try, which is just split the graph into 2 equal pieces in a way that you cut the smallest number of edges in between, right? This is called minimum bisection. And so if this is satisfied, then minimum bisection coincides with the true communities. You can recover them. And if it doesn't, then no algorithm works. Okay? It's not so hard to show a converse to this also. However, we are in this, right? So sort of the statistics information theory picture is completely understood at this point, at least for this simple model. This is completely the rule of when things work and when don't. However, unfortunately, minimum bisection is an NP-hard problem. So we don't expect that we'll be able to do this for very large graphs. Right? We expect that the best algorithm takes super polynomial time, perhaps exponential. And so we don't expect to be able to solve this for large problems. However, it turns out that in this particular case, exactly in the parameter regime where we care about finding minimum bisection, or at least in the one in which it works, turns out that minimum bisection can be computed efficiently. Right? So there's sort of a happy accident of sorts that, sure, the problem in the worst case is hard. The resulting problem, that would be the natural, say, the maximum likelihood estimator, the maximum output store estimator, and so on. In this problem, all of them coincide with minimum bisection. Is an NP-hard problem. However, exactly when it is sort of statistically meaningful, it seems to be also easy to compute. And of course, the natural question is, does this always happen? Right? Is it that sort of, even though the problems are in the worst case hard, for the instances that come from statistical problems, they're actually easy. And the NP hardness theory tells us nothing about it. So unfortunately, this doesn't seem to be always the case. And so I'll give you the classical, or now very classical example that illustrates why this isn't always the case. So this is known as the hidden clique problem. So this is a very similar style of problem. So here we're going to, instead of finding community structures, we're going to find a clique, set of nodes that's fully connected. So we have the underlying model is going to be an Erdős-Rényi model with probability half. This is just random graph whose each edge shows up independently with probability half, like uniform over all possible graphs. And now I'm going to give another model in which what I'm going to do is get the same, I draw again an Erdős-Rényi graph. The model is you draw an Erdős-Rényi graph with probability half, but then you pick k nodes at random, right? So not a great color. So you pick k nodes at random, let's say 4, and now you connect all those nodes, right? So you added a clique of size k. Okay. And now the question is, when is it that I can detect this clique, right? Or a similar question, which feels easier, but turns out is essentially the same question. If I give you a graph that comes either from this distribution or from this distribution, can you tell which one it is? Right, so I've sort of reduced this problem of finding structures to a problem of hypothesis testing. All you have to tell me is if we're in a state of the world where your graph comes from this distribution, or one in which your graph comes from this distribution, right? I reduced so-called estimation problem to a detection problem. I didn't mathematically reduce it. I intuitively reduced it, but this is okay. And so, of course, the first question one should ask is, what is the largest click on the left? Right, so it turns out you sit down, you work out the math, and the largest click is of size 2 log n, proving that it's smaller or equal than 2 log n is rather easy. And of course, on the right, there's a click of size at least k, because you just added 1. So if k is bigger than 2 log n, it should be very easy to tell the difference between these two graphs, right? Because this one, the biggest click is of size 2 log n. On the other side, the biggest click is way bigger if k is bigger, and so it should be very easy to detect. So around now, over 20 years ago, so Alon Krivolevich and Sudakov showed an efficient algorithm that works when k is bigger or equal than root n, right? Root n is much, much bigger than 2 log n. So the algorithm of just finding the largest click would be able to find the click at much, much smaller level sizes of clicks. Of course, that algorithm, that the problem of finding the largest click is also computationally hard. But there is an algorithm when k is bigger or equal than root n. And unfortunately, this has essentially been not improved ever since. Moreover, sort of we as a community believe so much that this is unimprovable that this is even used as a reduction primitive, right? An argument of the type, oh, your problem must be difficult because if you could have an efficient algorithm for your problem, then we could improve overall on Krivolevich Sudakov, and we really believe that we can. And so this suggests a very different picture from what we saw before, is what we call a statistical-to-computational gap, right? Where there's some notion of signal-to-noise ratio, right? So here you should think of signal-to-noise ratio as the size of the structure that I planted or the strength of the computed detection. I mean, I came to this because I was interested in imaging and in molecular imaging problems, and there you would really much more naturally call it signal-to-noise ratio, but it's just a measure of how easy the problem is. In which if you have too little signal, the problem is just impossible, right? If you have a lot of signal, the structure is very large, the problem is easy in the sense that you can do it efficiently. But it turns out, it appears that somewhere in between, the problem is statistically possible. So the picture from statistics information theory would say, yes, you can do this. But the picture from the computational side appears to say that you can't, right? And so it appears there's what we call a hard phase in the middle. So one of the things that I'm the most interested in trying to understand is, what does this hard phase look like mathematically for some of these problems? And do we have good ways of predicting where this computational threshold is? Because if we're going to be solving estimation learning problems with large data sets, we're certainly not going to be able to get into this hard phase. And the traditional theory of computational complexity won't help us, because usually the resulting problem will be just as NP hard in any part of this region. Okay, so there was a question.
Yeah, there is a question in the chat that whether the existence of a single click of size greater than square root n is enough to classify the two cases.
Yes, so if there is a click of size, okay, so depending how this question is being asked, so when k is bigger or equal than root n, it is easy to efficiently distinguish between these two. There's several algorithms. One, the simplest one is just look at the spectrum of the adjacency matrix. So having such a big click will transform the spectrum of the adjacency matrix in a way that you can easily detect. Maybe if you don't want to think about spectrum of adjacency matrix, although Dan would probably not be very happy if you decided not to think about that. But if you didn't want to think about that, then you could just count degrees. Basically, you're just adding enough edges. Like if you're if you're a bit bigger than k, you're sort of adding enough edges that it starts being on the size of the fluctuation of the total number of edges. So even by counting edges, you could sort of do it. Now, you could be asking another question, which is, could I not have a g_n plus a k click? Could I just have another graph with a size of a click of size root n, but I go and delete edges elsewhere and I do all sorts of things? Could I fool you? That's related to what I'm going to talk about in the end of the talk. Okay. So just to use it as a segue. Okay. And so the question that I'm interested in general is, how can we understand where where is it? How do we tell where is this computational threshold? Right? It's not about whether there's enough information in the data, right? It seems difficult to it seems difficult to answer this with measuring amounts of information. It's about whether sort of the information is easy to retrieve in a way. And so how do we go about answering something like this? Okay, so now that this is sort of getting to the end of my more general talk. So there's a few different ways of trying to answer this question. One is by looking at sort of the complexity of the posterior, the geometry of solution. Okay, so I'll use the stochastic block model example to try to make this point briefly. And here, one way to think about it is the following. So think back in this stochastic block model example, right? So these nodes have a hidden color, blue or red, say, right? You can think of them as hidden variables. They're plus or minus one, say one color is plus one, the other is minus one. And really what you're interested in is the posterior distribution of these labels given the graph that you see. Now, this is of course a random distribution over the hypercube. Right? Now, this is the kind of things that people have, physicists have been studying for decades. When they have lots and lots of particles, each particle has a spin plus or minus, and there's some statistical law for how these spins behave. And then you want to understand macroscopic properties of the material, such as like whether it's magnetic or not, right? Being magnetic sort of intuitively has to do with the spins all pointing in the same direction, or at least most spins pointing in the same direction. And so you can relate this random distribution over the hypercube to a certain object in statistical physics called a spin glass. And then it turns out that people in statistical physics have been developing tools to understand when is it that the distribution is complicated versus simple. Okay, I'm not defining any of this. And so you can use those tools to predict when is it that the posterior distribution of the node colors given the graph is simple or complicated. And turns out that this appears to give extremely accurate predictions of when the underlying inference problems are easy or hard. Maybe let me just convince you further of this analogy by saying that usually in physics, right, the dependencies between the spins are sort of local or very few particles at the same time. And here, if you think about this posterior, right, there's also has some form of product form in which the interaction between two nodes has to do with whether they have an edge or not. Okay, so I'll leave the analogy at this level. I'm happy to discuss it afterwards with more detail. Another class of methods asks the question of what if I restrict you to a certain class of algorithms? Okay. Of course, what we want to do is restrict ourselves to only efficient algorithms. But one can, of course, this is a very hard question. So we restrict ourselves to simpler class of algorithms that are easy to understand. Turns out an extremely useful thing to consider is what can we do if we restrict ourselves to low degree polynomials of the data, right? And so this is what the second part of the talk is going to be about. And there's many others. Maybe another one that I should mention is reduction, right? This seems a lot harder to do, although there has been some success in some cases, where you have one problem that everybody believes is hard, and then you say, if this problem is hard, then all these others are also hard, because if I had an algorithm for them, I could solve the original one. And planted click is usually used as this hard problem. Okay, but this is how NP hardness works for the most part. Now, the issue here is that because there is a problem and a distribution, you have to reduce both problems and distributions, and this seems very difficult in many cases. So if there's any questions, maybe I can take a 1-minute pause here to answer any questions as we switch to something a bit more technical. Okay, not, and I'll go for it. Okay, so now I'm going to get into one more a bit more specific example, and this is joint work with the YINS team and Alex, all of which are at NYU, which are amazing students and postdocs. And so I'm going to focus on the low degree, the restricting ourselves to low degree polynomials. Okay, so let me be a bit more precise about what I mean by this. So the idea behind this low degree method, so the motivation for it comes from, for those of you that are familiar with these things, it comes from sum of squares, right? This showed up explicitly in this really nice paper from Sam Hopkins and David Stoyer. And this comes motivated from the so-called sum of squares hierarchy. Let me not say more about that, but I'm happy to answer any questions. But we're going to restrict ourselves to this hypothesis testing realm, right? So there are only two possibilities. There's two distributions. You just need to distinguish between the two. And you should distinguish with error going to zero. The probability of failing should be going to zero. And you should view this as there being a null model, right? So this is like the graph without a planted clique, right? So I'm going to call this Q. And there is a planted model, right? In which there is some signal planted in the data. And this you should view, for example, as the Erdős-Rényi graph with a planted clique. And so you receive a sample Y. It comes either from the null model or the planted model. So either just noise or with signal. And you get asked, can you tell me which one it came from with probability going to 1 as the parameters of the problem go to infinity? Okay, so maybe take a second to digest this. So the reason you might ask, okay, why do you care about the error going to 0? It's because sort of being able to do estimation is related to being able to do detection or hypothesis testing with error going to 0. Having an error of sort of 10%, that or asking for hypothesis testing with an error of say 10% does not seem to be related to actually being able to learn or estimate. This is the right notion of error. And again, I'm happy to talk a bit more after.
Just a quick question. So it's not enough to say that with a little bit better than chance, I can say, and it is not possible to boost it?
No, because you get one sample only. Okay. Right? You get just one graph. Either it has the clique or either it doesn't. Now, yeah, okay, maybe I should say another. So in the stochastic block model case, you could ask a question of, can you guess the community structure in a way that your guess for the colors is better than chance? Right? This is an interesting question. This, however, corresponds to being able to tell if there is structure there to begin with or not, with probability going to 1. Because the point is, if you have something that is able to estimate, because of concentration of measure, even if the estimator itself has a performance that's just a bit better than random, it should have that performance consistently with probability going to 1. And so you could use it to be able to do hypothesis testing with probability going to 1. So there is this better than random on the performance, but on the probability for hypothesis testing, you really need it to go to 1. Otherwise, sort of, you can't say anything about estimation. Okay. Did it answer the question?
Yes, yes.
So, okay.
So Afonso, you mean going to 1 as n goes to infinity, or?
Yes, yes. So the probability of error should go to 0 as n goes to infinity.
Okay,
yes.
I missed that.
Yeah. Yeah, so all these little lows, and because it's always the n that's going to infinity. N is sort of the size of the problem. I mean, the size of the problem here really is n squared, but it's something that measures the size of the problem, and that thing is going to infinity. But yeah, thanks for the questions, because this is a point, right? I'm about to give lower bound. So it is important that I convince you that this little of 1 is the interesting case, right? Okay. So now the question is the following: is there a low degree polynomial of the data of y, f of y, that is big when y gets drawn from the planted case, from the case in which there's signal, and it is close to 0 when y is drawn from the null distribution? Okay. Now the key idea is to make this into an expression that we can actually compute with. And the idea is to try to find a polynomial that maximizes this expression, the mean under the planted distribution divided by the square root of the variance of the second moment over the null distribution. So because now this is something we can compute. So overall possible d-degree polynomials, I'm going to try to maximize the mean under P divided by the fluctuations under Q. So let me just convince you that this is something we can compute with. So let's do just a little bit of linear algebra, right? So this is what we want to find, okay? So we want to understand a bit what this is. So we're just going to do some change of variables to put all this under the null distribution, right? And the way to do the change of variables to taking expectations or integrals in the measure P to go to integrals in the measure Q is just to multiply by dp dq, of course. And so this has a name. This is called the likelihood ratio, right? This is the test from the Newman-Pearson test and so on. Okay, so now this is certainly equal to that. Now I have only integrals over the null distribution. Right now I can define, of course, this L2 inner product and norm over the null distribution. Right, so I define for two polynomials or functions in general. The inner product is just the integral over the null distribution of the product, right? And the norm is the obvious norm. So all this is just the maximum inner product of f with the likelihood ratio divided by the norm of f, right? But this is just a projection, right? The answer of this is clearly just the projection is just the norm of the projection of the likelihood ratio to low degree polynomials. Okay, the point is now we've created something that is just the projection in linear algebra, and so we're going to be able to understand it. Okay? And so so we just take the projection in L2 of the null distribution of the likelihood ratio on the subspace of polynomials of degree at most d, right? And the value is just the norm of this, the L2 of Q norm of this, right? And so while the idea of restricting to low degree polynomials comes in a certain sense from sum of squares and so on, right? This idea of this observation from Hopkins and Storer is quite consequential, because it turns out that this is now something we can compute, right, and make predictions of what we can say. Okay? So just to recall, so the maximum of this is the norm of this truncated likelihood ratio. Okay. Now, heuristically, what we should think about this, how we should think about this value is, if as n goes to infinity, this is going to infinity, then it suggests that this polynomial, or in particular degree d polynomials, can distinguish between Q and P, right? Because it suggests that the mean under P is of higher order than the size of the typical fluctuation under Q. If this is bounded as n goes to infinity, then it suggests that we can't, because the two things are of the same order. And so there is a conjecture that basically states this. Okay, I'm just going to mention it here informally, but it says for nice Q and P, then if this likelihood ratio, the norm of this likelihood ratio is bounded as n goes to infinity, where the degree you should take to be roughly log n, because this essentially corresponds to spectral algorithms. I'll say a bit more in a second. Then no polynomial time algorithm can distinguish between Q and P with success probability going to 0. We're going to 1. So that's the conjecture. This is not true for all distributions Q and P. You can hide certain algebra problems inside of these distributions, and then low degree polynomials will never be able to see it, right? And algebra like Gaussian elimination might, but for nice distributions P and Q, where you're not able to hide algebra problems inside, then this appears to be true, or I mean, appears to be true. We have no reason to believe it's not true, maybe is what I should say. And what you should have in the back of your mind is that degree d polynomials sort of correspond to n to the d time algorithms, right? That's roughly how long it takes to compute the polynomial. And you can make a more refined version of this conjecture where degree d polynomials should correspond roughly to time n to the d algorithms. Okay? And there is some rigorous evidence of why this conjecture may be true. So in particular, one can show that if, so in this case, when d grows bigger than log n, if you can argue that the likelihood ratio stays bounded, then no spectral algorithm can distinguish between these two distributions. And there's strong reasons to believe that spectral algorithms are just as powerful as sum of squares algorithms. And sum of squares algorithms are sort of the gold standard for average case analysis of these types of problems. Now, I will not.
Can I ask so do you mind going back to the last slide? So can you walk me through? Yes. Can you walk me through? So this low degree polynomial depends only on the distributions P and Q, and not any data that I have. So I can like compute it beforehand. When I have it, what is my test just to evaluate the function? Well, I guess let me ask this. Could you describe to me what the test is?
Yeah, so I haven't, and partly on purpose. You have a very good point, which is I'm not sure it's useful. I haven't found instances in which it's useful to actually compute this and actually try to evaluate this polynomial. I'm not sure I know in any interesting example how to compute this actual truncation polynomial. Turns out, however, that we can compute its norm. And so what I'm stating here is that given a problem, the test would be that you can compute, that you take this truncated, okay, so this is heuristic. I'm not saying that for sure with high probability, you're going to be able to find a cutoff for which this works. What I'm saying here is that the suggestion that if I'm more interested in the lower bound, if this is bounded, then this quantity must be bounded for any low degree polynomial. And so low degree polynomials should not be able to be a good statistical test. And then this leap of faith that polynomial algorithms also will not work. Okay. Now, the test itself, oftentimes, it's more like a spectral algorithm or approximate message passing or something of this type, which is well approximated by a low degree polynomial. So this sort of rules out a lot of algorithms that we know, because most algorithms that we know get captured in one way or another by low degree polynomials. Right? Because a lot of the algorithms that we know, they can be built as a spectral algorithm. By a spectral algorithm, I mean build a matrix whose entries are, say, low degree polynomial, and then look at the spectrum of that matrix. Now, interestingly enough, yeah, I'm not sure I know how to have an interesting case in which I compute this polynomial and we use it as a test and gain some new knowledge. However, we can compute its norm, and its norm predicts when the problem is easy or hard, and then the classical algorithms work up until when it's easy, and no other thing works when it starts being hard. So you should use this as a mechanism to understand when hardness happens, more so than actually suggesting an algorithm.
Awesome, awesome.
Okay. All right. Thanks for the question, though. Yeah. This is a point I should make more clear. Yeah. Thank you. So, okay. So let me just convince you that you can actually compute. So here's a class of models that I really like, known as the Gaussian additive model. So here, P and Q are relatively simple. Q, the null model is just a Gaussian on n dimensions, completely, uniform standard Gaussian. The planted model is you have some distribution for the signal X, and then you add that to your Gaussian. Okay? And so it turns out for this case, you can actually compute things. Okay, I will take advantage of the fact that this is recorded so that you can pause the slide and see the proof if you want, but the proof is uses some orthogonal polynomial magic, and then you arrive in a very nice expression. So it turns out that the norm squared of the likelihood ratio is given by this very nice expression. Okay? And so in the language of physics, the way you would read this expression is you take two independent replicas of the prior distribution. So you take a draw from the signal X, two draws, independent, X and X prime. The physicist would call it replica. You take the random variable of their inner products, which the physicist would call the overlap. Okay? And now you take the moment generating function of that, and you truncate it at degree D. And here truncation, I literally mean take the Taylor expansion of the exponential and just stop at degree D. Why doing truncation of this likelihood ratio polynomial corresponds to truncation of this moment generating function at the norm? It's not intuitive at all. It has to do with formulas that the orthogonal polynomials satisfy, but turns out in this case, this is exactly what it is. And now the point is that this is something we can compute in many examples. Turns out to be easy to compute. And for those of you that know things like Lecombe contiguity, chi-square divergence, and so on, right? This will probably be shouting Lecombe contiguity, because essentially, right, if I take away this D, right, I'm not restricting to degree D polynomials. I'm just looking at essentially any L2 function, right? Then this is exactly the kind of things that one compute when one is trying to understand Lecombe contiguity between two distributions and so on, right? And so this suggests in particular that if I don't do a truncation, then whether this blows up or not tells me something about whether the distributions are distinguishable or not. And then when I truncate, it tells me something about whether they're polynomially time distinguishable or not. And so hardness of distinguish appears to be at where the mass of these, right, of this moment in generating function is. Okay, and I'm happy to discuss more of this offline afterwards. Okay, so let me give you an example. Now I still have a bit of time. Okay, so here's an example I really like. So take the Wigner spike model. Okay? So here, what you have is you have your distribution is you have a random matrix, all independent entries, Gaussian entries, just conditioned to being symmetric. Okay, this is my matrix W, and my signal is just a rank 1 perturbation to this matrix. Okay, so I take lambda VV transpose and say V is uniformly distributed on the sphere, for example. Right? So this is inside the Gaussian additive model because, right, I can just view this as my X. It's distributed according to the law, pick V and then write lambda VV transpose, right? And W is just a standard Gaussian. Okay, you would just keep track of, say, the top triangular part or something. Okay? And so we understand a lot about this, right? We understand a lot about this model. We know that when lambda is bigger than this so-called the BVP transition, when lambda is bigger than 1, something pops out of the support. You see this eigenvalue that you or this eigenvector that you planted coming out of the support. There's sort of a lot of interesting things going on because, right, the actual largest eigenvalue of W is at 2, but already when lambda is 1, you start seeing something coming out. There's a very interesting phenomena happening in random matrix theory. But here, the question from our side is, when can we recover or detect V, right, from this, right? When can we detect that there was actually something planted? And this tells us basically then when lambda is bigger than 1, of course you can detect because it's right here. If not, then probably we can't. And one can indeed show that statistically it's impossible. Below lambda 1, it is impossible. But now what we're going to ask is, what if we put more structure on the vector V? Do interesting things arise? And so for those of you that are more familiar with thinking in terms of Wishart matrices and planted the problems in PCA and so on, the exact same story that I'm about to tell holds for the planted model in Wishart matrices. It's exactly the same. It's just a bit easier to explain this over Wigner matrices. Okay. So now let's go to something called the sparse PCA problem. So the sparse spiked Wigner model, in which I tell you furthermore that this vector V that is planted is no longer uniform on the sphere, but it's actually sparse. Okay? So it is rho n sparse with rho smaller than 1. Okay? So it has few non-zero entries. And because I'm in the business of giving lower bounds, I'm even going to tell you more, just to make things easier. It's actually going to be just either zeros or plus or minus 1s, normalized to have norm 1, right? And it's going to be rho n such entries. So the smaller rho is, the more structure is there in my signal, the easier it should be to learn, right? And now you can ask, if I let rho go down, can I recover? Even though it doesn't show up in the spectrum, something fishy in the matrix should be apparent, right? If I somehow, there should be an eigenvector in the top of the spectrum of this matrix that is too sparse, that shouldn't happen just by chance. Okay? And indeed, this is true. So already at a constant level of sparsity, it is indeed possible to detect even when it doesn't show up on the spectrum, like even when it doesn't show up here as an extra eigenvalue. Right? However, you basically have to do it by exhaustive search over all sparse vectors, and so this takes you exponential rho n time. If you want to do it efficiently, there's algorithms that do it efficiently, but require a sparsity level that's much, much lower. You need to be at root n sparsity. And there's lots and lots of evidence of computational hardness, reductions to plenty of clique, restrictions with class of algorithms, and so on and so forth. This is a really nice test problem to try to understand these types of phenomena. Now, you can, of course, just test this tool on it and see what does the low degree predict here, right? And so now what we're going to be testing again is the planted distribution, in which you plant a spiked vector, right, with its outer product with itself, and another where you just have a Wigner matrix. You work out the calculations, and what you see is if the degree is smaller or equal than rho square n, then the likelihood ratio is bounded. If not, then the likelihood ratio goes to infinity with n. So what you deduce from here, if you believe the conjecture, is that exploiting rho n sparsity essentially needs degree rho square n, right? So you should think of, you're at lambda smaller than 1, so you're below where the thing shows up in the spectrum, right? Where if you had no sparsity, you would not be able to do it. And so it seems like exploiting rho n sparsity requires exponentially rho square n computation, right? Because degree d should correspond roughly to polynomials of time exponential in d. Now, the interesting thing here is that this is different than this, right? Like exhaustive search would take exponential rho n, which is potentially a lot bigger, right? If rho is a polynomial in n. But then if you go look, there's actually an algorithm that takes exponential rho square n. After you know that this is the right computational complexity, it's actually not so hard to find the algorithm. And in fact, there's another algorithm in the literature from around the same time that achieves exactly this runtime as well. And no better is known, right? So the point here is that it appears that this method is not only telling you which problems are hard or not, but actually understanding exactly how much, what is the sub-exponential complexity of these problems, right? I'm interested in understanding if these methods are capturing the hardness or not. And so the more precise predictions I can make, the easier it is for them to potentially be falsifiable, right? And here it's making a very, very precise prediction of exactly how much computational power is needed. And it seems to match exactly what we see in algorithms that exist, and nothing better exists. Right? So now let me talk about, do I have maybe 5 more minutes or 7 more minutes? How much?
Yes.
Yes, okay, all right.
I give you 7 more minutes.
7 more minutes, good, thank you. So, okay, so what I talked about was mostly statistics so far. So what, right, and hypothesis testing, what does this say about optimization? Okay, and so it turns out that this says something about optimization. It's not a very classical question to ask in optimization, but I would argue is an interesting one. So let's look at the Sherrington Kirkpatrick problem. Okay, so optimization of the Sherrington Kirkpatrick Hamiltonian. So what I mean by this, I take W to be a Wigner matrix. Again, Gaussian independent entry, symmetric, and define the SK of W as this optimization problem. Right? If you're an optimizer, this is just a random quadratic program. Right? X needs to be plus or minus 1. I'm just normalizing it here so that these things don't depend on n. And you're just maximizing the quadratic, a random quadratic polynomial on X with Gaussian coefficients. Right, and now we can ask, what is the typical value of this optimization problem? We can ask all sorts of questions. Is it difficult to optimize? It's not, and so on. So we know, let's look at what we know about this Wigner matrix. We know that the maximum eigenvalue is 2, right? The maximum eigenvalue of a Wigner matrix is 2, right? Just from here, this is of course smaller or equal than if I maximize not necessarily over the hypercube, but just I maximize overall L2 norm 1, or let's say equal to 1, it's 2. Right? If instead of maximizing over the hypercube, I just maximize over the ball, for sure I'm going to get something bigger, right? And this is exactly this 2, right? So for sure it's smaller or equal than this. Now we can try to approximate it from below, right? A random guess gives 0. If you just give random X, you get 0. And then over the years, there's been many improvements. Okay, so let me show you first the algorithms, right? So random guess gives 0. If you do some greedy iteration, you stop at 1.064. If you round the leading eigenvector, so you do the optimization over the sphere and then you round to plus or minus 1, you do a bit better and so on. So the right value was obtained from work of Parisi, then and from the statistical physics side with non-rigorous techniques, and then was made rigorous later. The right value is this Parisi constant, is 1.526, and amazingly, we now believe that actually you can get arbitrarily close to it with the polynomial time algorithms. This is sort of an algorithm that really knows a lot about the problem. It's very specifically designed for this problem. Okay? And it's still, the fact that it gets all the way to the optimal answer is still conditioned on a certain conjecture, but a very believable one. Okay? But the question I'm trying to ask here is different, and is the following: can we close this gap? So what I mean by close this gap, can we give an upper bound to this, but a certified upper bound? So what I mean by this is, given W, can we come up with a function f of W that is always bigger or equal than SK of W? This needs to hold pointwise, right? So lambda max of W is such a function. Okay. And now I evaluate how good it is, say, in expectation. Right, these quantities will concentrate very, very quickly. So we're asking in expectation, high probability, all these things are the same. Okay, so I ask for a function f that is always bigger than SK of W, and I want to evaluate how good of an upper bound it is in saying expectation, right? So I evaluate how good of an upper bound is on the Wigner measure, but I need it to be an upper bound always. So this, I mean, you might, right? One might argue that this is another type of question from approximating from below. Maybe a motivation that I should mention is that sum of squares is sort of the gold standard for understanding average complexity and a lot of this, and sum of squares is of this type, right? So by understanding what are the limits of this, you're effectively in part understanding limits of sum of squares as well. And of course, I want to do this with an efficient. I want F to be computationally efficient, right? Because otherwise, I could just make F of W be SK of W. Okay? So the leading eigenvalue of the Wigner matrix is such a function, so I can get to 2. The question is, can I do better? Like the sum of squares do better. The sum of squares degree 2 do better. Degree 4 do better. Degree 6, and so on and so forth. And so now we believe that it is impossible to do better in this sense. So that there is a sort of a different type of computational gap in this problem that is giving upper bounds for this problem, or certified upper bounds, is intrinsically difficult. Okay, and there's many different kinds of evidence. I'll talk a bit. There's in particular, one can compute what sum of squares would give for at least some degrees. And I will give you what the indirect evidence looks like, because that uses statistics in a certain way. Okay. So how do we argue that there is a gap here? We build another distribution, W tilde. Go ahead, sorry.
A question. This 1 point in the previous slide, 1.5. This is an ugly number, right?
Yeah, it's like the fixed point of some equation.
I see. Okay, so there is no actually clear thing.
It's 2p star. No. Yeah. It's the fixed point of some equation and so on. Yeah. It's not. I mean, so the conjecture that will imply that the NP algorithm from Andrea Montanari gets all the way to here, essentially is that this problem is very complicated. It satisfies a so-called full epoch symmetry breaking without an overlap gap. I can talk about this after the talk a bit more, but basically this problem should have a very, very complicated landscape, but somehow not have big barriers that you can still make progress. Okay, I'll leave it at that, and then we can talk a bit more offline. Okay, so how do we argue that there is indeed a gap? We build something called a quiet planting. So you build a distribution, W tilde, okay, and we'll call this distribution a quiet planting. And this distribution satisfies the properties. First of all, the value of SK for W tilde is close to 2. And secondly, doing hypothesis testing between a true Wigner and a W tilde is, we believe, computationally hard. Okay, so basically I hid a very low minimum of this, or maximum, I think I mentioned the problem in the maximum of this SK, and I argue that this is not detectable in polynomial time. And so what this means is that, if there was a way to upper bound better than 2, then such an upper bound could be used to distinguish between these two distributions, right? Because it's clearly would give at least 2 for W prime, and if it was an upper bound better than 2, it would give less than 2 for W. So if we believe that the statistical question of distinguished distribution is computationally hard, then this implies that there is no algorithm that can give a certificate better than 2, and in particular, it would imply that all these hierarchies of relaxation and so on, they cannot possibly give better than 2. Okay, the point is, an upper bound certificate needs to be correct for all matrices W, gets evaluated only under the Gaussian measure, right? So it can be very pessimistic sometimes, but it can never be too optimistic. Is the construction clear? I realize this is not so easy to swallow the first time you hear it. And so how do we do this? So, the spike models don't quite work here. You need to sort of mess with the spectrum of the Wigner matrix. Okay, so I'm happy to answer any questions about this. Now, the reason why it's interesting that you sort of have to mess with the spectrum of the Wigner matrix is that you can now ask these kinds of questions for graphs, but it's very hard to mess with the spectrum of a graph and make sure that it's still a graph. And so a very nice question over graphs is, what bounds can you give on the chromatic number of a deregular graph? So if I have a uniform deregular graph on n nodes, I ask about its chromatic number. We know that the typical value for the chromatic number, and we'll concentrate very well around it, is d over 2 log d. Okay. And here's the picture that we have now. So I'll go straight to the picture for sake of time. Right. So searching for callers, if you want to search for a caller efficiently, we believe, right, this is work that dates back a few decades. We believe that you need at least double the callers. So somehow search stops here. Right. So the right number of callers needed is this. If you want to search a caller, and you need double the callers. If you want to certify a lower bound on the chromatic number, right? What is to certify a lower bound on the chromatic numbers? I give you a graph and you come up with a proof that I could not possibly color it with less than a certain number of colors. Maybe you find a clique of size that plus 1, right? Right. So the natural certificate is so-called a Hoffman bound, is basically a lower bound given by the minimum eigenvalue of the GCC matrix. Okay? The natural way of trying to plant low chromatic numbers, so to plant small colorings, is with basically the stochastic block model. So it turns out that this doesn't get there. There's a bottleneck. And the gap is created exactly because of these issues with the spectrum. The reason why this doesn't get here is exactly a BBP phenomenon, a BBP spike model type phenomena, this push out effect, that somehow when you go here, the thing you're planting with the stochastic block model starts perturbing, the noise starts interacting with the signal and starts to create something that then you can detect. Okay? I'm not being very precise, but I'm happy to talk a bit about it more. So now that we know that what we have to do is go massage the spectrum, turns out that we can make a planting, so-called equitable stochastic block model, where basically we make sure that spectrally, the noise and the signal don't interact with each other. And so we can plant all the way to the Hoffman bound. Okay? And so the Hoffman bound is optimal in this sense, and you cannot do certification or lower bounds on the chromatic number better than root d over 2. Now, as a word for sort of maybe more for the experts, this doesn't quite work for every degree exactly. So it's true as degree goes to infinity, but you can formulate the same things also about the propounding sizes of cuts. But this equitable model only works when certain integrality conditions, like the chromatic number needs to divide the degree typed conditions, is satisfied. When it's not, this doesn't quite work. Now, when things go to infinity, those things start being neglectable, but for small ones, they don't. And so it turns out that for small degrees, we can actually find, by virtue of failure of these techniques, we can actually find better certificates for very small degree. They have to do with properties of, essentially of certain Ramanujan graphs and so on. I'm happy to talk about this a bit offline afterwards. Okay, and this is it. Sorry if I took more time than I should have. I'm very happy to stick around and discuss and answer questions. And hey, thanks again.
Thank you very much. Yeah, we are right at 1 o'clock, so people can actually leave to their classes. I have asked all the questions that I had. I don't know whether there are other pressing questions that people would like to ask.
Maybe if I can ask something, Afonso. This is Dan Kushner.
Yeah, go ahead.
So Afonso, in most of it's a high level question, kind of. So most of the problems you addressed are sort of, as learning problems, we probably can call them unsupervised problems, right? There's many situations in which you can have what we call a side information, or maybe some supervision on this side. So how would you address this setting? I mean, is this setting, essentially looking at different SNRs in this setting, or is the SNR the same, but how would you formulate this hardness when you also have some type of, or maybe you can quantify some side information that you can bring into your problem?
Yeah, so this is a very good question. So you can do some things in some supervised problems, like in certain regression type problems. It's hard to reduce them to hypothesis testing questions, but you can still apply some of the techniques even outside the hypothesis testing. So here I'm focused very much on what we call detection, right? So we're just detecting if something is on the data or not, and then we reduce to hypothesis testing. I think once you have side information, it's probably more interesting to not reduce to detection, because probably detection might start becoming too easy, because the side information probably becomes very, very easy to detect. Or there's many problems in which this is the case. There's some reason for why actually detecting if there's something there is very easy, but finding it is still hard. And then you need to actually understand the limits of estimation. So I think I haven't thought much about side information, but certainly in some like regression type settings, this happens when somehow your planted signal has a positive expectation. Maybe you're planting like the sparse signal you're planting only has positive entries, say. In this case, in order to get interesting results, you should try to study estimation directly. And then for estimation, there's basically, so now there are adaptations of the low degree technique for estimation. So by Alex Vine and Sil Schramm have a new paper that's a very nice idea to adapt the low degree method to estimation, where you don't ask if you can do hypothesis testing, but you ask, can the low degree polynomial correlate with the signal that you want to estimate, say, things of this style. There's another very nice structural property, which is called this overlap gap property, which basically is a structural property on the space of solutions. As you're searching for your solution, you can view it as sort of a barrier that doesn't allow you to go through. And you can show that some of these problems have this so-called overlap gap property. And then if you have side information, you can view in some cases as sort of starting a bit closer to the solution. And then you can ask yourself, did I go already over the barrier or not? And this should tell you if you have enough side information or not. Mm-hmm. I mean, I could talk about some more specific examples, but in this sort of search, in the search problems, you can incorporate like a warm start, for example, and the quality of a warm start.
Okay, thank you.
Thanks for the question. Yeah, I mean, this is a very good point for sure. Yeah, and yeah, maybe a good example to look. There's some work on sparse linear regression, for example, that has some of these features.
Okay, thank you.
Okay, very good. I'm actually going to send you a different link so that we can, if you have time, we can chat for a few minutes.
Okay, yeah, happy to. Sure.
Okay, great. Thank you. Thanks a lot for having such a good lecture, and thanks for everyone who attended. And of course, they should follow up with you and your papers if there are more questions.
Yeah, happy to answer. I mean, just write me an email. Happy to get on Zoom whenever and talk for sure. Yeah.
Cool. And hope that
Thank
next
you.
time you can actually visit us physically.
Yeah, me too. Yes, hopefully. Yeah, for sure.
Okay. Take care.
All right. See you. Bye.
Yeah.